Hi, my name is Brian Still, and I'll be presenting the paper today, Lock It and Still Lose It, a paper on the insecurity of automotive remote keyless entry systems. First of all, I'd like to acknowledge the original authors of this paper, Flavio Garcia, David Oswald, Pierre Pavlidis, all from the University of Birmingham in the United Kingdom, and also Timo Kasper of Kasper and Oswald. This paper was originally presented at the 25th USENIX Security Symposium in Austin, Texas in 2016. If you're interested in this paper, please feel free to reference the link provided below to the original paper that was presented. First, a little bit of purpose and objectives for the researcher's presentation. First of all, primarily the background or motivator for this paper was that there has been over the many years automotive immobilizers, which are the components that allow your car to start or not start, have been proven to be insecure for several years, which led to the introduction of remote keyless entry systems, and as such, those remote keyless entry systems have received very little attention from a security perspective since that time. The researchers are going to present vulnerabilities in these keyless entry systems, in particular how easy they are to be exploited, how many vehicles that are vulnerable, and we're going to deep dive into two specific algorithmic families that are particularly vulnerable and have widespread use within the vehicle industry. Those are the VW Group algorithm, which is originally developed by the Volkswagen company and used in Volkswagen cars, and then the HiTag2 algorithm, which is a next generation remote keyless entry algorithm that we'll discuss. This paper has several applicabilities, one of which is surprisingly that many times insurance cases from locked vehicles have been claimed and believed to be fraudulent due to the nature of the claims. However, because of this paper and the ease of which these systems can be exploited, whether or not those claims are fraudulent should be re-examined in the sense that many of the claims of the vehicle owners may turn out to actually be true. So let's start into it. For many years, physical keys were used in automobiles. They required no electronics, and it required physical access to the car and to the key in order to unlock the doors or to start the ignition. These locks were very easily picked, and locksmith tools are readily available on the internet, Amazon, Walmart, and so it's very easy for a motivated attacker to be able to pick a lock or to break into systems where physical keys are involved. And so that led to the evolution of remote keyless entry. A typical remote keyless entry device is based upon RFID technology, and it includes a small microcontroller built into the head of the key, along with an antenna and other RFID circuitry. Typically, it includes two components, an immobilizer, which enables an engine to start, and that needs to, typically the immobilizer component needs to be within about a 6-inch range of the corresponding vehicle component that is receiving that signal. And then there's the remote keyless entry, or RKE component, and that's used to lock and unlock doors, initiate a panic button, and also unlock hatchbacks, and it can work within a several meter range between the vehicle and the key. There's also a next generation of keys called passive keyless entry and start, or PKES, and these require proximity to the vehicle within about 3 to 5 feet, and a bidirectional challenge response scheme in which the key and the vehicle both initiate challenge response schemes to verify authenticity between the key and the engine. When the challenge response is successful, that enables the car will unlock doors, deactivate alarms, and actually enable the engine to start. The key thing that makes the PKES different from the RKE is that it does not require user intervention, i.e. you don't need to push buttons, just be in close proximity. And this actually makes them very prone to relay attacks, whereby the proximity to the vehicle is no longer required if an attacker is able to use an amplifying signal or relay device between the key and the vehicle. And those such attack tools are available on the black market. Surprisingly, PKEs are also typically more used on luxury cars and more modern cars, which actually makes them more susceptible to such attacks. If you were able to look inside the PKE, you'd see some of the same components that are in the RKES, particularly the key component being a small microcontroller, as shown in the diagram to the right. In this paper, the researchers were able to build an analysis tool that they used to deconstruct the wireless signals, but also to be able to reverse engineer some of the algorithms and the capabilities and the firmware of these remote keyless devices. Pictured on the left is such a device that the researchers built. It's based upon an Arduino software-defined radio. These are commonly available in the market. By adding a few inexpensive RF modules within the relevant frequency bands and adding a 9-volt battery, you can build one of these components for approximately $40. The capabilities of this simple device were actually quite extraordinary, namely that the ability to eavesdrop on signals between keys and car, to be able to record those signals, to be able to emulate a key press of an RKE, and to also perform what is called reactive jamming. During the analysis and the reverse engineering, the RKE packet analysis was performed to essentially reverse engineer and see and determine the RKE packet structure. The packet structure is shown there on the left, and it consists of a preamble, a start pattern, a payload, and a checksum. The preamble and the start pattern are fairly consistent for each time a button is pressed or each message. The preamble and start pattern are identical. The two parts that change are primarily the payload and the checksum. The checksum is just a direct, simple checksum of the payload. So really the payload is the key component of the message, and we'll focus specifically on the payloads. In the payload, there are 2 or 3 primary fields. The first is the unique identifier. This is an identifier that uniquely identifies and pairs each key with the actual corresponding vehicle it's associated with. And so in both cases, they would each have the same UID or unique identifier. The next key thing is the rolling counter or some type of rolling counter. This is a counter that essentially is incremented each time a button is pressed or each time an acknowledgement exchange is performed between the key and the car. And what this does is it keeps synchronization between the two, but it also adds has a tendency to add a little bit of randomness, if you will, to the actual message between the two. And then the last component is which buttons were physically pressed, and this is typically 1 bit per button, where each button would be like a lock or unlock or alarm type indicator on the device. So looking into the Volkswagen algorithms, there's actually an evolution of 4 Volkswagen algorithms. They're all fairly similar in nature. Their researchers refer to them as VW1 through VW4. Each of the algorithms were fairly similar to each other. They had some variations and evolutions as time went on, but they still had some of the same capabilities. There were differences in the RF frequency and some of the modulated signal encoding and bit rates between each of them, but generally speaking, it was the same message format and the same capabilities between these 4 algorithms. So we're going to look into each one of these one at a time. In the VW1 algorithm, the payload structure consists of the fields that are specified below. The unique ID, the LFSR, or linear feedback shift register. This is that counter that we were discussing before, and so it is used to synchronize between the car and the key. And so each time a button is pressed, one of the corresponding bit for that button is set within that button field, and the LFSR is incremented, and of course the UID is always the same. What makes this particular algorithm very susceptible is its simplicity. You can see that there's no encryption on this particular packet. It's sent as it is there, and it's very susceptible to a modified replay attack, where you could essentially just increment the counter and know how to use it the next time. So an attacker, if he were able to listen in and intercept this particular packet, it's just a matter of incrementing the LFSR, knowing the next count, and then just retransmitting it, and he can control the buttons as if he was owned the original key. In the VW2 and VW3 algorithms, there was some additional encryption that was added to the algorithms. And so in this particular case, you still have the unique ID, a counter, and a button and an inverted button that was used as a kind of a confirmation, if you will, double check. But the algorithm actually took several a byte at a time and ran it through various combining functions and permutations using the AUT64 block cipher and a 32-bit key. The problem with this particular case is that there's also within the VW algorithmic group, there is a global master key, and it can be reused. So instead of if an attacker wanted to take control of a vehicle that through the RKE interface, then it's just a matter of knowing what that unique user ID is, filling it into bits 24 through 56, and it really doesn't matter any of the other information. The global master key is used, and it can be used on any Volkswagen RKE system worldwide. The VW4 analysis actually added some additional complexity and replaced the AUT64 cipher with an XTEA cipher. Now this cipher was computationally more intense. It's a 64-round Feistel structure, and it actually would be a 128-bit key, which makes it very infeasible in order to be able to crack this particular encryption code. However, it also has the same problem as the VW2 and 3, which is there's a global master key. And so it's far less easier to know the global master key, inject that into the stream, and generate the appropriate response, and you don't need to crack the actual encryption code. So looking at the VW group of algorithms, successfully gaining the master key can decrypt all current counter and user ID values. And so this makes all of these algorithms potentially weak if that master key is known. Now the researchers were able to discover the master key by actually reverse engineering the software or firmware of the ECU, which is the car component onboard computer. By reverse engineering that, they could easily find the global master key and use that to brute force any of the algorithms, especially the VW2 and 3. There's some other interesting side effects that were noted in the paper. Using the counter more than 2 increments behind disables the remote entry. And so you could actually use, by injecting or generating incrementing counters to the car, an attacker could essentially perform a denial of service on the vehicle, such that the RKE would become out of sync with the car, and button presses on the actual vehicle owner's RKE would not work. If you fall 2 or less increments behind, puts the remote out of step. And that actually is a case that works, but it does require the button to be pressed, at least twice or more in order to open the locks. And if you've ever had this occur, that indicates that your car may have actually been tampered with using such an attack surface. The only recommendation of the researchers for valid countermeasures is to use the physical locks. There really is no countermeasure, as it's the vehicle provider and manufacturer is not willing to fix these algorithms and replace millions of cars and onboard computer systems with new technology. And the surprising thing about this is that there's nearly 20 years of Volkswagen vehicles that are vulnerable to this attack on the roads today. Our second algorithm, the HiTOG2 algorithm, it has a rolling code system, and it was designed not by Volkswagen but by a company called NXP, and it is not known to use global master keys. And so this makes it more secure in that sense than the VW algorithm. However, it is possible to crack after just 4 to 8 button presses. And so this is where the Arduino analysis tool comes into play, where to be able to capture at least 4 to 8 button presses in order for that to be easily cracked. The algorithm itself goes through many key stream and blocks that are initialized through the values that are shown below. But essentially, on each clock cycle, there's 20 bits of the LFSR that's put through a filter function, producing 1 bit of key stream. And then the LFSR is shifted 1 bit to the left, and then a polynomial feedback algorithm is used to generate a new bit on the right. So the way to crack the HiTOG2 algorithm is called a correlation attack, and it goes something like this. The first step is to guess 16 bits corresponding to the LFSR. Initially, if you can follow the algorithm, A32 through A47 is the first 16 bits of the key stream. And if you know the UID, you actually have all the bits A0 through A47. And so you've already gotten a significant component of the final stream. Then for each, you compute a correlation score for each guess. And there's a ratio of about 2 to the 12th input values of X8 through X19 that produce key stream 0. And the guess is independent of an initial vector. You then sort all guesses according to the score. And then for each guess in the table, repeat the above steps, extending the window size by 1 from size 17 to 32. So why does this attack work? Well, first of all, it uses the window on the right of the LFSR to compute the key stream bits to correct the internal state. Again, recall that you have 4 to 8 samples to begin with, and you can use to correlate. It then combines the multiple traces using the window on the left of the LFSR to get the correlation information on the multiple key stream bits. Another key component of this is that there is a 28-bit counter that's used in the cipher, but 10 of those bits are actually sent over the air, so you know the 10 of those bits. The remaining 18 bits are the most significant 18 bits of the 28-bit counter. However, those upper 18 bits only increment every 2 to the 10th counts. And so if you know the usage of the key and how old the car is, you can typically guess within 1 or 2 what those upper most significant bits are. And that is used to be able to greatly limit the the values that need to be looked at in those upper 18 bits. So the researchers, by using this correlation attack, were on average able to crack the HTOG2 with a typical laptop in about a minute. Their worst case maximum crack time was approximately 10 minutes when they had no idea what the LFSR MSB counts were. And so again, one of the keys to this is that being able to guess the 18 most significant bits of the counter, which was typically a very low value. The researchers concluded that both RKEs are vulnerable, both in the Volkswagen group, primarily due to the use of a global master key, and that you can crack usually with just one recording of a button press. You can crack those algorithms. The HTOG2 is also vulnerable, but it was more so in a flaw in its cryptography and the weakness in the ability to guess and the upper 18 bits of the LFSR counter, but also knowing the UID, which was flowed into the key that was used into the key stream. And it typically only took 4 to 8 button presses to crack. And there were about 20 years of vehicles that are vulnerable to both of these attacks. The manufacturers and models year of car brands that are affected by these keys are listed there on the left. And as you can see, there's while quite a many of those are Volkswagen, part of the Volkswagen family, some of them are not. The owners of the analysts and researchers of this paper, wanted to affirm that and prove that the RKE and PKS systems are widely vulnerable to attack and primarily theft. And that this includes personal belongings, where attackers are able to unlock doors and take things that are inside the car. Infotainment systems, radios, VCRs, things of that nature were also high target items and easily stolen using these exploits. And of course, the automobile itself could easily be stolen. The researchers, while didn't confirm, they did suggest several possible safety issues in the sense that a compromise could also, of the ECU that controls brakes and other driving functions, could be compromised. It could be used to lock someone in their car by jamming or otherwise intercepting the car lock mechanism. And then also on-the-road robbery. This would be a carjacking type scenario where the vehicle driver believed that the car was locked when in fact the attacker could unlock the door using these exploits. One of the main concerns is that theft may remain undetected for a longer period. There's no physical traces, there's no fingerprints, there's no jammed lock or picked lock in these kind of things, and the car systems itself do not record it. One possible mass scale attack was proposed in that an attacker could put up devices such as the Arduino described in the parking lot and could eavesdrop or even relay RKE and PKS systems such that car doors would unlock without the owner's knowledge, or they could be replayed at a later time. Also, the user or the attacker could use the Arduino system or a similar system to be able to increment the counters such that the vehicle owner's remote keyless entry systems would not work due to the counters being out of sync, and could actually cause a dealership or a manufacturer's customer service department to be overloaded with requests for new keys or reprogramming of keys. Also, the insurance industry has implications. In many cases, cars were stolen or merchandise or belongings were stolen from inside of a car, and the insurance company could not find any evidence of wrongdoing or breaking into the car. And so they were categorized, a lot of these cases, as fraudulent. which ruined some or affected some of their clients' rapport. And so one of the statements that the researchers made was that some of these cases may in fact be real. They were using some of the vulnerabilities and attacks that we've discussed today. And in summary, the owners or the researchers provided the warning that if you're an owner of an affected vehicle that has this technology, the really recommendation was to stop using the RKE and PKES systems and fall back to mechanical locks. The RKE and PKES systems are very weak from a vulnerability standpoint and provide no significant or no real protection if you have valuables in the car or would like to keep your car. The authors also wanted to make sure that the vulnerabilities were reported to the VW Group systems and NXP, and so they responsibly disclosed these vulnerabilities to the manufacturers. And while neither manufacturer provided any resolution for these two problems, both received the disclosure very well and are investigating and rolling in additional capabilities in future products. Thank you for listening, and thank you for this presentation. If you have any questions, feel free to post those questions on Piazza under the appropriate heading. Thank you once again.